Okay, so you know how people think matrices are like just this super dry math thing?
Yeah, definitely.
But they're actually kind of a secret weapon behind so much of what we see and do every day.
Totally. It's kind of mind-blowing when you start to realize it.
Like, think about your favorite spreadsheet software.
Right.
You know, when you're like putting together a budget or projecting sales, you're basically working with matrices.
Absolutely.
Right.
It's all about that structured data.
But it gets even more interesting, right? When you zoom in on a photo or rotate something on your screen.
That's matrices in action.
Yeah.
Yeah.
Those are actually matrix operations happening behind the scenes.
And it goes way deeper than
Oh,
that.
yeah.
It's like from cryptography to genetics, economics, sociology,
Wow.
even modern psychology, and how huge industries manage their operations.
That's incredible. It really is everywhere.
It's a truly universal tool, and in ways you might not expect.
Which brings us to why you, our listener, shared Chapter 3 from lem103.pdf with us.
You want to get a handle on the fundamentals of matrices and matrix algebra.
Right, and you don't want to get bogged down in a bunch of technical jargon.
It can definitely feel overwhelming at first.
So consider this deep dive your fast track to the essential insights, a way to cut through the complexity.
Exactly. We want to break down this chapter in a way that's clear, insightful,
Right.
and hopefully leads to those aha moments.
Absolutely. We'll be exploring what matrices actually are, the different forms they can take.
And how they behave when we throw some basic math operations at them.
Okay, so let's unpack this. The chapter kicks off with a very simple idea. Imagine we want to jot down that Radha has 15 notebooks. We could just write it like this. 15.
Straightforward enough.
Now, what if she has 15 notebooks and 6 pens? We can represent that as 15-6.
Okay.
The position of each number tells us what it represents.
Right.
If we swap them around, 615, that would mean something different, wouldn't it?
Precisely. This is the core idea behind a matrix. It's about arranging numbers in a way that gives them meaning.
That makes sense. Now, let's say we want to track notebooks and pens for Radha and her friends, Fauzia and Simran.
Okay.
The source shows us we can organize this in a table. So we have Radha with 15 notebooks and 6 pens, Fauzia with 10 notebooks and 2 pens, Simran with 13 notebooks and 5 pens.
Makes sense.
Now we can take this table and represent it as a matrix.
Right.
We could put the students as rows and have notebooks and pens as our columns.
Or we could flip it around.
Exactly. We could have the items as rows and the students as columns, but once we choose an arrangement,
Right, like if we decide students are rows, items are columns.
that order becomes super important for anything else we want to do with that data.
Absolutely. Consistency is key.
Okay, so now for the formal definition. A matrix is defined as an ordered rectangular array of numbers or functions.
So it's all about that rectangular shape.
Right, and those numbers or functions are called the elements or entries of the matrix.
In sense.
And we usually use capital letters to name our matrices. The source gives us a few examples. Matrix A is full of regular numbers, matrix B has decimals, and matrix C even has trig functions.
So it's not just about simple numbers. It can get more complex.
Exactly. But for this chapter, we're mainly focusing on real numbers and real valued functions.
Okay, that simplifies things a bit.
Right. Now, within these rectangular arrays, we have horizontal lines, which are called rows.
And vertical lines, which are columns.
You got it. So in the source, matrix A has 3 rows and 2 columns. Matrix B has 3 rows and 3 columns. And since the number of rows and columns is the same, we call this a square matrix, something we'll come back to.
Okay.
And matrix C has 2 rows and 3 columns.
So we can see the different shapes they can take.
Exactly. Now, the number of rows and columns gives us what we call the order of the matrix.
The dimensions, basically.
Right. It's written as MAN, where M is the number of rows and N is the number of columns.
So like going back to our examples, A would be a 3x2 matrix, B is a 3x3, and C is a 2x3.
You got it. And to figure out how many elements a matrix has, you just multiply the number of rows by the number of columns, M times N.
Easy peasy.
So whenever you, the listener, see a matrix written as AMN, the MAN tells you the size and structure of the matrix.
Right. And A refers to a specific element in that matrix.
Exactly. Like it's giving you an address for each number in the grid.
I tells you the row number, and J tells you the column number.
Now here's a cool connection that starts to hint at the power of matrices. A point in a 2D plane, like XY, can be represented as a matrix.
Oh, interesting.
We can write it as a column matrix, like XY, or as a row matrix, XY.
So a single point can become a matrix.
Yeah, like point P at 0, 1 can be written directly as a matrix.
That opens up some interesting possibilities. What other kinds of information do you think we could represent with matrices?
That's a great question. It gets even cooler when we talk about shapes.
Oh, really?
Yeah. The source shows how the vertices of a polygon, like a four-sided figure ABCD, can be put into a matrix. Imagine each corner has specific x and y coordinates.
Right.
You could have a matrix, let's call it X, where the first row has all the x coordinates of the corners, and the second row has all the y coordinates.
Okay, so each row is like a specific coordinate.
Exactly. Or you could have another matrix, say Y, where each column represents a vertex.
Oh, I see. So the x-coordinate would be on top of the e-coordinate for each corner.
You got it. So instead of a list of points defining the shape, we have a single organized structure, a matrix, that holds all that information.
That's really neat, and I bet it becomes super useful when we want to do things to those shapes.
You're reading my mind.
Hmm.
Moving them, rotating them, scaling them. It all comes down to matrix algebra. But let's take a step back and talk about the different kinds of matrices we might encounter.
Okay, good idea.
We've already talked about square matrices where the rows and columns are the same,
Right.
but there are other important types defined by their structure.
Let's start with a simple one, the column matrix. It's just a single column.
Okay, easy enough.
The source gives an example of a matrix with 4 rows and just one column. The general form is HEM-A1, where Iman can be anything, but there's always just one column.
Got it. And then we have the row matrix, its horizontal counterpart,
Exactly. One row, any number of columns.
like a matrix with one row and four columns. And the general form would be Bajai1 AN.
Okay, that makes sense. Now back to those square matrices where m equals n, we just call it a square matrix of order n.
Right.
The source shows a 3 by 3 square matrix as an example. And in any square matrix, there's this special set of elements called the main diagonal.
Oh, yeah, the diagonal from top left to the bottom right.
Exactly. These are the elements where the row and column indices are the same. So the first element of the first row, A11, the second element of the second row, A22, and so on, until you reach an in an NXN matrix.
The source shows exactly which elements are on that diagonal.
Now, building on that, we have the diagonal matrix, special type of square matrix. All the elements that are not on the main diagonal are 0. The elements on the diagonal can be anything, but everything else is 0.
So the source shows diagonal matrices of different orders, like 1 by 1, 2 by 2, and 3 by 3.
Exactly. And then we have a specific kind of diagonal matrix, the scalar matrix.
What makes that one special?
In a scalar matrix, not only are all the off-diagonal elements 0, but all the elements on the main diagonal are equal to each other.
Oh, I see. So they're all the same constant value.
Exactly. Let's say k. So you have k all along the diagonal and zeros everywhere else.
Like in the source, where they have examples with K being 3 in one matrix and last one in another.
Right, and from there we get to the very important identity matrix.
Which is?
It's just a scalar matrix where that constant k is equal to 1.
Oh, okay.
So it's a square matrix with 1s along the main diagonal and zeros everywhere else.
So it's like the neutral matrix for multiplication, like the number 1.
You got it.
Yeah.
We use n to represent the identity matrix of order n, or just I, if the order is clear.
And the source shows us I1, which is just 1.
I2, a 2 by 2 matrix with 1s on the diagonal.
And I3, the 3 by 3 version.
And it's important to note that every identity matrix is also a scalar matrix.
But not all scalar matrices are identity matrices.
Exactly. A scalar matrix is just an identity matrix that's been scaled by some value, k.
So an identity matrix is a scalar matrix with K equal to 1.
Precisely.
And last but not least, we have the zero matrix.
Simple but important.
Yeah, all its elements are 0. We use the letter O to represent it.
Okay.
And the source shows 0 matrices of different sizes.
So we've seen all these different types, but they all have that rectangular array structure at their core.
Right. And knowing these different patterns will be really helpful when we start doing operations with them.
Definitely. Like, before we dive into adding and multiplying, we need to understand what it means for two matrices to be equal.
Right. It's not just about them looking similar.
Exactly. There are two conditions. First, they have to have the same order, same number of rows, and same number of columns.
Makes sense. If they're different sizes, they can't be equal.
Exactly. Second, each element in the first matrix must be identical to the corresponding element in the second matrix.
So if we have matrix A with elements A and matrix B with elements Bj,
Then for A to equal B, A must equal Bj for every single I in J.
so like the top left element in A has to be the same as the top left element in B, and so on.
Right. The source shows us pairs of matrices that are equal, And also examples where they're not equal.
either because they have different orders or because some of the elements don't match up.
And it also shows how we can use this definition of equality to solve for unknown variables within the matrices.
Oh, that's interesting. So if we know two matrices are equal,
We can set up equations by matching up the elements.
I see, and then solve those equations to find the unknown values.
Exactly. The examples in the source start with a simple case where you just directly compare elements and then move on to a slightly more complex scenario
Yep.
where you need to set up a system of linear equations.
Okay, now let's finally do some operations on matrices, starting with addition and scalar multiplication.
Let's get our hands dirty.
The source uses a great real-world example here. It talks about Fatima, who has two factories that produce sport shoes,
Okay.
and she wants to figure out her total production of shoes across both factories.
Makes sense.
This is the perfect setup for matrix addition.
Oh, I see.
Imagine each factory's production is represented as a matrix, with rows for different price categories and columns for shoe types.
Oh,
To find the total production, we just add the corresponding entries from the two matrices.
so like you add the number of low-top shoes from factory A to the number of low-top shoes from factory B and so on.
Exactly. But, and this is super important, you can only add matrices that have the same order. Same number of rows, same number of columns.
It's like adding apples and oranges. You need the same units.
So formally, if we have two matrices, A and B, both of order mxn, their sum C A plus B will also be an mxn matrix.
Okay.
And each element in C, let's call it Cj, is just the sum of the elements in the same position in A and B. So Cj equals A plus B.
Got it.
The source goes through a numerical example to illustrate this. And remember, if the matrices have different orders, you can't add them. It's undefined.
Makes sense.
Now, the source also mentions that matrix addition is a binary operation on the set of matrices of the same order.
What does that mean exactly?
Basically, it means that when you add any two matrices of the same size, the result is also a matrix of that same size. It stays within that same space of matrices.
Oh, okay. So it's like a closed system. You always end up with the same kind of object.
Exactly. Okay, so now let's talk about scalar multiplication.
All right.
Let's go back to Fatima. Imagine she decides to double production at her first factory.
Okay.
How do we represent that change in matrix form?
Interesting question.
This is where scalar multiplication comes in. A scalar is just a regular number.
Right.
To multiply matrix A by a scalar k, you just multiply every single element in A by k.
So you just scale up the whole matrix.
Exactly. And the resulting matrix, Ka, will have the same order as the original matrix A.
Okay. Makes sense.
So in Fatima's case, doubling production would be like multiplying her production matrix by the scalar 2.
Oh, so every entry in the matrix gets doubled.
You got it. Now, the formal definition is this. If A is an mxn matrix and K is any scalar,
In our case, a real number.
right, then Ka is also an mxn matrix, and each element in Ka is K times the corresponding element in A. The source has a numerical example where they multiply a 2 by 3 matrix by the scalar 3.
So you just triple every element in the matrix.
Exactly. Now, building on this, we can define the negative of a matrix.
Oh, how to do that?
The negative of a matrix A, written as ev A, is simply minus 1 times A.
So you multiply every element by -1.
You got it. And this lets us define the difference between two matrices, A, B.
Okay, so A minus B is the same as A plus -1 times B.
Exactly. Like with addition, you can only subtract matrices with the same order.
Right.
You just subtract the corresponding elements of B from A.
Makes sense.
The source works through an example of calculating 2AB.
So you double all the elements of A, then subtract the elements of B.
Precisely. Now that we can add and multiply matrices by scalars, it's natural to ask, do these operations follow the same rules as regular numbers?
That's a great question.
Like, does the order we add matrices matter?
Interesting.
And the source does a good job of outlining some key properties of matrix addition and scalar multiplication.
Okay, good.
So first, for matrix addition, we have the commutative law. It states that if A and B are matrices of the same order, A plus B is always equal to B plus A.
So the order you add them in doesn't matter.
Exactly. The source gives a little algebraic justification for this based on the fact that regular number addition is also commutative.
Okay, that makes sense.
Then we have the associative law for matrix addition.
What's that one?
So if we have three matrices, A, B, and C, all the same order,
Okay.
then A plus B plus C is equal to A plus B plus C. It doesn't matter how you group them when adding.
Oh, okay. So like if you add A and B first, then add C, it's the same as adding B and C first, then adding A.
You got it. And this property stems from the associative nature of real number addition.
Makes sense.
The source actually encourages you to think about why this holds true.
Oh, that's a good challenge.
It's a great exercise for understanding how the individual elements are being manipulated.
Definitely.
Now, there's also this concept of an additive identity, like
Okay.
how adding 0 to any number doesn't change the number.
Right.
There's a zero matrix with all entries equal to 0 that works the same way with matrices.
I see. So if you add the zero matrix to any matrix A, you get back A.
Exactly. A plus O plus A will A.
Got it.
And every matrix A also has an additive inverse.
What's that?
It's negative A.
Oh, okay.
When you add a matrix to its additive inverse, you get the zero matrix.
So A plus negative A equals the zero matrix.
Exactly. A plus A plus A plus A plus A.
That makes sense.
Hmm.
Now, what about scalar multiplication? Does that have any special properties?
It does. We have some distributive properties at play here.
Tell me more.
First, if K is a scalar and A and B are matrices of the same order, then Ka plus B is equal to Ka plus Kb.
So the scalar distributes over the sum of the matrices.
You got it. The source shows the algebraic steps involved. And second, if K and L are scalars and A is a matrix, then K plus LA is equal to Ka plus LA.
So here, the sum of the scalars distributes over the matrix.
Precisely.
Interesting. It seems like these properties really mirror how we work with regular numbers.
They do. These properties all come from the way real number arithmetic works.
Makes sense.
Now, the source also shows us how we can use these properties to actually solve matrix equations.
Oh, how do we do that?
Imagine you have an equation with an unknown matrix X and known matrices A and B, along with scalar multiplication and addition.
Okay.
You can use the properties we just talked about to isolate X, just like you would in a regular algebraic
So
equation.
you add inverses, multiply by inverses of scalars, and so on.
You got it.
This seems like a really powerful tool for solving more complex problems.
It is. Matrix equations let us represent and solve systems of linear equations which pop up everywhere in the real world.
That makes sense. So instead of having a bunch of separate equations, we could put it all into one neat matrix equation.
Exactly. And it gets even better. You can solve systems of matrix equations where you might have two or more equations with two unknown matrices, like X and Y.
Oh.
You solve it similar to a system of regular linear equations.
Oh, I see. So you can manipulate the equations to eliminate one of the unknowns and solve for the other.
Exactly. The parallel with regular algebra is really helpful for understanding what's going on.
It definitely makes it seem less intimidating.
Right. We also see an example where we need to find unknown scalar variables within the elements of a matrix.
Oh, how do we do that?
You set up a matrix equation, do the scalar multiplication and addition,
Okay.
and then use the definition of matrix equality to equate the corresponding elements.
So you end up with regular algebraic equations that you can solve.
Precisely. It's all connected.
I love how it all ties together.
Now, for a real-world application of all this, the source gives us a scenario with two farmers, Ramkishan and Gurcharan Singh.
Okay.
They sell 3 different types of rice in September and October.
Makes sense.
Their sales figures are given as matrices A and B.
So each matrix represents a month's worth of sales.
You got it. This example shows how matrix operations can be used to analyze real data.
That's cool. How so?
Well, A plus B represents their total combined sales for each rice variety.
Okay.
AB shows the difference in sales between the 2 months.
Interesting. So you can see which varieties sold better or worse in each month.
Exactly. And if you multiply matrix B by 0.02,
That would be their profit margin, maybe.
you got it. It's a 2% profit margin on their October sales.
So you can calculate profits for each farmer and each rice type.
Precisely. It's all about applying those basic matrix operations to get meaningful information.
Wow, matrices are surprisingly versatile.
All right, we've added and scaled. Now for the operation that really makes matrices shine. Matrix multiplication.
Oh yeah, this is where things get more interesting.
This is where we go beyond element-wise operations.
And it's key to understanding the true power of matrices.
The source uses another relatable scenario to introduce it. It talks about Mira and Nadim buying pens and storybooks from 2 different shops.
Okay.
Each shop has its own prices for these items.
Makes sense.
This example perfectly captures the logic of matrix multiplication.
How so?
Well, think about it. We can put the quantities of items each person bought into one matrix,
Okay.
maybe a row matrix for each person.
Right.
And then we can put the prices of each item at each shop into another matrix.
Maybe with items as rows and shops as columns.
You got it. Now, to find the total amount each person spent at each shop.
We'd use some kind of multiplication in addition?
Exactly. You multiply the number of each item by its price and then add those products up.
So if Mira buys a certain number of pens and storybooks,
And we know the prices of those items at shop 1.
to find her total cost at shop 1, we multiply the number of pens by the pen price, the number of storybooks by the storybook price, and add those two results.
Precisely. And matrix multiplication takes this idea and applies it to larger sets of numbers in a specific way.
That makes sense. So it's like a systematic way of doing those calculations for a whole bunch of values.
Exactly. And this brings us to the formal definition of matrix multiplication.
Okay.
For the product of two matrices, A and B, to be defined, there's a super important condition.
What is it?
The number of columns in the first matrix, A, must equal the number of rows in the second matrix, B.
So the inner dimensions have to match up.
Exactly. If A is an MXN matrix and B is an NXP matrix, their product C equals AB will be an MXP matrix.
I see. So the number of columns in A has to match the number of rows in B.
Right. And to calculate each element in the resulting matrix C.
Okay.
Let's say we want to find the element in the ith row and kth column, which we'll call sick.
Right.
We take the ith row of A and the kth column of B. Multiply the corresponding elements from that row and column.
And then add up all those products.
You got it. It's a row by column operation.
So the source gives a formula with summation notation for this?
Exactly. It shows exactly how to calculate each element, and then it walks us through a detailed example of multiplying two matrices, C and D.
So you can see exactly how it works with real numbers.
Right. It shows how each entry in the product matrix CD is calculated step by step.
Which row from the first matrix is combined with which column from the second, and how those element-wise products are added.
Exactly. Now, another example shows us how to find the product AB for two given matrices.
Okay.
But here's a key point. Matrix multiplication is not generally commutative.
Oh, what does that mean?
It means that just because you can multiply A by B to get AB,
Right.
it doesn't necessarily mean you can multiply B by A to get BA.
Oh, interesting.
And even if you can multiply them in both orders.
The results might not be the same.
Exactly. In some cases, the dimensions might not even work for BA to be defined.
Us?
Like in the previous example where BA is not defined at all.
Okay.
And even when both AB and BA are defined,
They might not have the same order. Right.
you got it.
Yeah.
Like if A is an MXN matrix and B is an NXM matrix where M and N are different.
Then AV will be a square matrix of order n.
And BA will be a square matrix of order N.
So they're different sizes.
Exactly. But get this, even if AB and BA are defined and have the same order,
What happens then?
they're still not necessarily equal.
Oh, wow. That's surprising.
It is. And the source shows this in example 13.
Okay.
They use a 2 by 3 and a 3 by 2 matrix.
All right.
And they show that AB, which is a 2 by 2 matrix, is not equal to BA, which is a 3 by 3 matrix.
Well, they're different sizes and their elements are different.
Exactly. And example 14 takes it a step further. It uses two 2 by 2 matrices.
So both products are defined and have the same order.
Right, but their elements are still different.
Wow. So AB is not always equal to BA, even when they're both possible?
Exactly. This is a huge difference from regular multiplication where the order doesn't matter.
Yeah. 2 times 3 is always the same as 3 times 2.
But with matrices, order is everything.
It can totally change the result.
Now, here's another thing that might seem strange.
What's that?
It's possible to have two matrices, A and B, where neither of them is a zero matrix,
Okay.
but their product, AB, is a zero matrix.
Whoa, really?
Yeah. It's shown in example 15 in the source.
So you can multiply 2 matrices that have non-zero elements and end up with a matrix full of zeros.
Exactly. This never happens with regular numbers.
Right. If you multiply 2 non-zero numbers, the result can't be 0.
It's one of those things that makes matrices unique.
It highlights that matrices behave differently than regular numbers.
Right. Even though they're made up of numbers, they have their own set of rules.
So it's like a whole new kind of algebra.
Exactly. Now, even though matrix multiplication is a bit funky,
Yeah.
it still has some important properties.
Okay, good to know.
First, the associative law still holds.
Remind me what that is again.
It means if you have three matrices, A, B, and C, and all the products are defined,
Okay.
then ABC is equal to ABC.
So the grouping doesn't matter when multiplying
Yep.
multiple matrices.
As long as you keep the order the same.
Right.
Second, we have the distributive law.
Okay.
AB plus C equals AB plus AC.
So you can distribute matrix multiplication over addition.
Exactly.
Yeah.
And it works the other way, too. A plus BC equals AC plus BC.
So matrix multiplication is distributive.
You got it. And finally, we have the multiplicative identity, which we talked about with the identity matrix.
Right.
If A is a square matrix of order n,
Okay.
and you multiply it by the identity matrix n, either on the left or right.
You get back the original matrix A.
Exactly. In A equal A in it A.
It's just like multiplying by 1.
Now, the source gives us examples 16 and 17 to show these properties in action.
Oh, that's helpful.
Example 16 uses specific matrices to verify the associative law.
So it shows that ABC really does equal ABC.
And example 17 verifies the distributive law.
Okay.
It shows that A plus BC equals AC plus BC.
So they demonstrate that these properties hold true for specific cases.
Exactly. You don't have to go through all the calculations right now, but it's good to know they're there.
Definitely. It helps to see concrete examples.
Now, example 18 introduces this cool concept called polynomials.